Hi, I'm KR, and this is my Motion of Falling Objects lab. The purpose of this lab is to observe an object in motion falling with force of drag and force of gravity. The models we'll be using is free body diagrams, glow script, and tracker. The physical principles is Newton's second law and the kinematic equations, and the preview results is that the predicted model with drag will be very similar to the actual model since the drag is accounted for in the calculations. This is a video of falling object through tracker. The systems and assumptions. The surroundings are made up of the ground, which is the origin, and the force of gravity, a force of drag from air resistance. The system is the paper ball. As you can see here with the free body diagram, the force of drag is pushing up on the force of gravity. I did not achieve constant terminal velocity, so the force of drag is slightly smaller than the force of gravity in this situation, and the force of drag is also variable. We're assuming that the only forces acting on the paper ball is the force of gravity and force of drag. Assuming the paper ball falls straight down, so only in the y-axis, there is a non-constant net force acting on the paper ball, which is the force of drag, or F net, once you subtract force of gravity from force drag. And due to Newton's second law, F equals ma, F net is equal to force drag minus force of gravity, which is the main principle in this lab since we are calculating how the forces, or how the variable, the non-constant force, is affecting the ball while it's falling. So the initial conditions is 0 meters per second in all directions. The force of gravity is 0.4905 newtons, and I'll show later on how I got that calculation. The floor is the origin, and the initial position for the ball of paper, which is my system, is 1.022 meters in the y direction. So my calculations using Newton's second law, I got F net is equal to F force of drag minus force of gravity. Force of drag is equal to B, which is constant, times the velocity squared times the unit vector velocity. Force of gravity is equal to mg, and then I'm using the position update formula and the velocity update formula for glow script. So this is the observed position. Using tracker, I calculated or I plotted the position of each point at each second to get my track position height. Using this equation I have here is the polynomial curve. It allows me to get the F net at any time using the second derivative of that equation, and I have my plotted points and my curves for the tracker position. So the ball with gravitational force, this is the calculations with using glow script. I only placed the force of gravity on the ball, and it gave me it passed through the origin a lot faster than the ball without with force of drag. As you can see here, it passes through the origin a lot sooner, and it goes to the negatives for position. The ball with gravitational and drag force, the using F net and F drag equations, I was able to calculate the predicted position. It's very similar or very close to the actual position, and using again glow script, I did this calculation using update velocity and equation and the position update equation. The conclusion of this lab is that the predicted position versus time graph for the gravity reaches the origin or ground faster than either the predicted position versus time graph for the gravity and the drag or the observed. So basically, as you can see here, the predicted position for FG on the graph is reaches the origin a lot faster. It gets into the negatives a lot sooner than either the observed position or the predicted position for with accounting for force gravity and force drag. And the observed position has a lot more of an arc compared to the predicted position. I'm assuming this is because of some small variables I didn't account for due to turbulence. Possible errors were when using tracker and having to plot the positions by hand, I might have gotten off a few pixels, and this would affect the force of drag slightly in my models. So what does this mean, and what if? When an object reaches terminal velocity, so the forces acting on the object for force drag will have to equal force gravity to get an F net of 0 because terminal velocity is constant velocity. And so that means F drag and force of gravity would equal each other. And what if the object had an initial negative velocity? The object will still reach the same terminal velocity, since force of drag is equal to is like proportional to the velocity. So as you can see here on the chart, if you had a higher negative velocity, you would just start off later in the graph. Eventually, the forces again will balance, since force of drag is proportional to velocity. It will eventually equal, and this you'll reach terminal velocity earlier. Thank you.